Okay, so this is an introduction to torque, and my name is Dr. Clyde Letzum. And for this video, what I'd like to do is go over torque in general, the introduction of torque, talking about the basics of torque, by going through a definition of torque, diagrams, demonstrating torque, applications of torque, then talk about conditions for torque equilibrium, and then look at a torque equilibrium example. All right, so let's go ahead and begin by talking about the definition of torque. So torque, and we use the Greek letter tau to represent torque, is a measure of how much a force tends to rotate an object about a pivot point, or we can call that pivot point a point of rotation. That force that causes the rotation is the force component perpendicular to the moment arm of that object. And what exactly is a moment arm? Well, the moment arm is that distance between that point of rotation and the point where the force is being applied. Okay? We may use the following equation to calculate the torque of a system. Torque is equal to force times the distance between, again, the point where we're rotating about that pivot point and the point where the force is being applied. When it comes to the metric system, we measure torque in units of Newton meters. Okay, Newton meters. So that's our basic units that we use when we talking about torque, the units for torque in a metric system. Okay, so now in this diagram, we've heard the definition of torque, but that was just a definition. So let me give you a graphical example of what we're talking about. So we have this force that's being applied here to this object. This object is affixed at this point right here. And so the moment arm, or the distance between the pivot point and where the force is being applied, is given by the letter D. Okay, and again, the object is affixed to this point right here. So if it's affixed to this point and everywhere else it's not fixed, okay, and a force is applied at the end here, then what happens is this object has a tendency then to rotate going in this direction. Similarly, if we look at the diagram over here where we have this object and it's affixed at this point and this point only, and we have then the distance between the point of rotation and where the force is being applied, that distance there. That distance is D again, and this represents the moment arm, and the force is being applied here. What this does again is it causes the object in this case to now rotate going in this direction. Okay. All right, so now that you've gotten a graphical representation of that, let's talk about a practical application of. So let's say we have some nut that we're trying to turn, let's say off of a tire or something, and we grabbed a lug nut. Okay, that lug nut, okay, or the not the lug nut, but pardon me, the torque wrench, okay, has a distance from where we're applying the force, which is over here, to the point of rotation, which is around the actual nut. And that distance is represented by D. The moment arm is represented by D here. And again, the force is being applied here. If I want to increase the torque on this nut here, there's two things I can do. I can either increase the force that's being applied here. Now, in many cases, that's not um, feasible. Okay, let's say if you're trying to take off the uh, nut off of a tire, that may not be feasible. So if you can get a longer lever arm also, lever arm or moment arm, you can also increase the torque on the nut that you're trying to take off. So again, if you're trying to take off that nut, there's two things you can do. You can either get a longer lever arm, or you can apply more force, and that would allow you to be able to turn that nut that is stuck on your tire. Okay, so now that we've talked about torque and we've talked about the definition of torque and we've looked at some practical examples and some diagrams, Now let's look at conditions in which conditions for torque equilibrium. Okay, so let's say so an object for torque equilibrium. So let's define that. An object is at equilibrium when it has no net force acting on it. That is, if an object has no net force, then it will not move or rotate. So given that that's the case, what we're actually saying is that the summation of the forces acting on the actual system should be equal to zero. And if that's the case, then what that means then is that the summation of torques should be equal to zero. Because remember, torque is composed of forces, right? Okay, so now that we understand that, let's look at this diagram here that demonstrates the conditions of equilibrium. So in this diagram, we have this bar here that's going all the way across, and this bar is actually affixed at the center point right here. Okay, now the distance from the center point to where a force is being applied, the force number one is being applied, is represented by D1 here. That distance is represented by D1, and the force is being applied here. We'll call that F1. And if we have another force that's being applied over here, and that distance between the force and the point of rotation is equal to D2, then in order for us to have equilibrium within this system, and by the way, F2 is going to try to spin the bar this way, and F1 is going to try to spin the bar that way. In order to make sure that this system is in equilibrium, so in other words, no spinning, no rotation is occurring, then we need to remember that torque has to be equal to zero. If torque is equal to zero, then what we're saying is when we sum up the torques, okay, the torque 1 and torque 2, both of those have to be equal to zero. So if that's the case, then we know that torque is equal to force times distance. So we can replace torque 1 here with F1 times D1. And you'll notice that there's a minus sign here. That minus sign represents that the distance that we're looking at is actually in a negative x direction. So what we're thinking about is we're thinking about this fixed point right here as being our axis. And so therefore then this is in the negative x direction. Okay. Now F1, since it's pointing upward, straight up, that means it's going in the positive y direction. So that's why F1 is positive and D1 is negative. And so now we add that now to F2 times D2, and F2 is again in the positive direction, and D2 now is in the positive x direction. And all of that again should be equal to zero. So what we do is we go ahead and, whoops, let's go back a little bit. What we go do is go ahead and bring the negative sign from there, from here out here. And so we can continue to manipulate the equation so that we get that F2 D2 times D2 is equal to F1 times D1. Okay, or flipping it around, it's the same as saying F times D1. F1 times D1 is equal to F2 times D2. Now what that is simply saying is that the torque on this side has to be equal to the torque on this side. And so that's why I flipped it around over here, just to illustrate that this has to be equal to this. Okay, so you can think of this system as having a line going down the middle here and saying everything that's on the left side has to be equal to everything that's on the right side. Okay. Okay, now given that that's the case, let's go ahead and look at a very similar system. In this case, instead of the forces pointing upward, now the forces are actually pointing downward. Okay, forces are pointing downward. And again, we're going to use this. This broken line here to say that everything over on this side needs to be equal to everything over on this side in order to prevent the bar here from rotating. Okay, so given that that's the case, then we again remember torque, the summation of torque has to be equal to zero. And so then that is to say that torque 1 plus torque 2 has to be equal to zero. And negative F1 times negative D1 plus negative F2, let's bring that up, negative F2 times D2 all has to be equal to zero. In this case, we have negative F1 because the force is pointing downward. We have negative F2 because this force is pointing downward. We have negative d because this is in the negative x-axis. We have positive d because d2 because this is in the positive x-axis. Okay, and so that's why we get the signs that are here. And if we do negative times negative, this ends up being positive. If we do negative times positive, this ends up being negative. And so therefore we can go ahead and continue to manipulate the equation such that we end up with F1 times D1 is equal to F2 times D2. Okay. All right. So now that we understand that, now let's look at a torque equilibrium example. And in this example, we're given the following diagram. So this is our diagram here. And in the diagram, it says that F2 is equal to 8 newtons. F3 is equal to 5 newtons. And pardon me, F2 is equal to 8 newtons, that's over here. F3 is equal to 5 newtons, and the question asks us what would F1 have to be in order for us to have a system that is in equilibrium. Okay, now the distance between F2 and the pivot point is equal to D. The distance between F3 and the pivot point is equal to 2D, and distance between F1 and the pivot point is equal to 2D also. Okay, so now given that that's the case, we know that again, in order for us to have equilibrium of torque equilibrium, the summation of torque should be equal to 0. That is to say, torque 1 plus torque 2 plus torque 3 should be equal to 0. Now, given that that's the case, let's go ahead and write our equation out a little bit more complete for that. So that then would be negative F1 times negative 2D, 2 times D, plus negative 2, negative F2 times D plus negative F3 times 2 times D is equal to 0. Okay. Oh, and one thing I want to mention here, you'll notice that I'm using x's here and I'm using multiply or the star here. There's a reason for that, and I'll elaborate on, or I'll talk about that actually in the second video. It's not as important to your general physics type classes, but it's a little bit more important towards your principles of physics or your calculus-based physics, and we'll talk about that in part 2. But any which way, just consider this multiplication and this multiplication to be exact same thing. And again, all of this should be equal to 0. All right. And so now we go ahead now and again, negative negative gives you positive, negative positive gives you negative, negative positive gives you negative. And so that's why we have the sign changes here. And so let's go ahead and make sure that now both of these go over to this side. Okay, just as we have those two forces over on this side and we have F1 on this side. Okay, and again, remember we're solving for F1. And so therefore then this is what we have at this point. Okay, now we can factor out the D from all of those terms and we end up with this as our current equation when we factor out the D. And we can divide both sides by D, which gives us this. Okay. So now you can see that we know what F2 is equal to. We know what F3 is equal to. The only thing that we don't know is what F1 is equal to. So we need to isolate F1 by itself on this side. In order to do so, what we're going to need to do then is divide both sides by 2, which we've done in this step. And so F1 is equal to F2 plus F3, and F3 is multiplied by 2. All of this now is going to be divided by 2. And so now we can start to plug our numbers in. And so what you'll see then is that F1 is equal to 8 plus 5 times 2. Remember, 5 times 2 has to be done first. And all of that is going to be divided by 2. So that comes out to be 5 times 2 is 10. 10 plus 8 is 18 divided by 2. And so we end up with F1 needs to be 9 newtons in order to make sure that this does not rotate. Okay? All right. So that was the introduction to torque. Please do look for part 2 of the torque discussion, and that's going to be on my YouTube channel. Again, my name is Dr. Clyde Letzum. Please do check out my website, clydeletzum.com, or check out my YouTube channel at youtube.com/CA Letzum PhD PE. Thank you.